particularly for the last I would say the origin is basically I would say from a paper in 1981 by a person by name Herbert Gleiter. Okay. So, Gleiter is from Germany, can be considered as a pioneer in the nanomaterials, and they have made nanomaterials of various metals and ceramics starting from 1981. The initial properties of general materials once you take them to a nano regime. So, if you look at the mechanical property of any polycrystalline material, we usually correlate the mechanical property to the grain size, okay, with a relation called the Hall-Petch relation. You all are aware of it. So, which looks something like this, that if you plot the grain size as a function of d to the power minus half, okay, you get a straight line relation. Okay, this is commonly known to all of us. So, when the d to the power minus half increases, that means if the d is decreasing, then you have an increase in the strength, and this is basically attributed to the grain boundaries acting as the pinning agents for the dislocation motion. This is all known to all of us. So, if you have more number of grain boundaries, by decreasing the grain size, you have more obstacles for the dislocation movement, and as a result we say there is a decrease, there is an increase in the strength, yield strength of the material, or stress required for the further movement of the dislocation, which is basically the yield strength of the material. So, if you extrapolate this to the 0 d to the power minus half, what does it basically mean? When you are extrapolating it to the 0 d to the power minus half means what kind of a material it is? Glass. Is it it is? It's a single crystal. Yes. When the d to the power minus half is 0, that means you have the largest crystal possible, and which is a single crystal. So, as a result, if you look at the intercept of the yield strength, sorry, the y axis has to be the yield strength of the material or the stress required for the deformation. The yield strength of the material, if you look at what is the intercept, that is what we usually define as sigma ys as sigma 0 plus k into d to the power minus half. This is a standard Hall-Petch relation, where the sigma 0 is nothing but the intercept on the y axis, which you can call it as the yield strength of a material when the grain size is very large. But in principle, when you make a single crystal, okay, a single crystal most of the time what we produce have almost 0 dislocations, or usually whenever a single crystal is synthesized, it usually is nucleated on one of the screw dislocation and it grows. That is what people usually observe whenever a single crystal is grown by any of the techniques such as Czochralski technique and things like that. Okay. So, if you look at most of the single crystals, okay, the number of dislocations are very few. When the number of dislocations are very few, then how do we attribute the Hall-Petch relation to such a material where the grain size is very large? In principle, the Hall-Petch relation says that the strength should decrease and come to a very low value when the grain size is very large and when it becomes a single crystal. But at the same time, you will see that when it becomes a single crystal, that its number of dislocations being so small, Hall-Petch relation itself cannot really work, because Hall-Petch relation is based on the dislocations being pinned down by the grain boundary. Okay? If there are no dislocations or there are very few dislocations in a material, okay, in principle we cannot really use the Hall-Petch relation. So, as a result, in principle this plot, when you approach 0, should increase and then goes to a value which is much higher, which is what we call it as theoretical cohesive strength of the material. Okay. So, that is what exactly happens when you go to very small number of dislocations which are usually observed in crystals which are single crystals. So, basically Hall-Petch relation has a limitation when it is being used for a material which has no dislocations or very few dislocations. So, single crystals really utilizing a Hall-Petch relation is very difficult. Okay. So, one has to remember this limitation when we use a Hall-Petch relation. Similarly, on the other side, we are talking of nanomaterials. Okay. When we go to nanomaterials of very small sizes, we end up again in a similar situation. Okay. You think of a nanomaterial of a 5 nanometers, let us say. Imagine a material, a grain of a 5 nanometers. Okay. So, in a 5 nanometers, how many atoms you can expect in any particular direction? What is the usual interatomic distances in a metal like aluminum, let us say? What is the usual interatomic distance? Or if you think of a lattice parameter for an aluminum, which is nothing but the A parameter, what is the approximate value? Anybody remembers? In terms of nanometers or in terms of angstroms? Do you know? It is about 3 to 4 angstroms. Most of the interatomic distances in metals are about 3 to 4 angstroms. Okay. So, if you look at such a interatomic distance, okay, assume it to be around 4 angstroms, and if you take a 5 nanometer material in any particular direction, you can't expect more than about 12 atoms or 15 atoms. If you think of 3 dimensions, okay, you have such a material of about 10 to 15 atoms in a particular direction. In such a material, how many dislocations you can really expect? We know that whenever you have 2 dislocations, 2 of different kind, let us say unlike dislocations, there is always an attraction between any 2 unlike dislocations, and then they ultimately merge into each other. Okay? And then a dislocation vanishes. If you consider a like dislocation, any 2 like dislocations, there has to be a minimum distance between any 2 like dislocations, isn't it? Because of the repulsion between the 2 like dislocations, there has to be a minimum distance, and this minimum distance is usually of the order of 4 to 5 interatomic distances. So, if you think of about 5 interatomic distances, you cannot expect in a particular direction more than 2 or 3 dislocations in a material of about 5 nanometers. So, if you really go to such fine scale of nanomaterials, the number of dislocations itself are so few that one can really talk about dislocations being obstructed by the grain boundaries. So, in principle, in a number of cases, there have been a few examples also where people have seen that there is a lattice softening that occurs. Lattice softening occurs basically because when you have a large grain boundaries, okay, the material flows like a viscous material, okay, because the grain boundaries are something like an amorphous structure or like a liquid structure. So, when you have such a disordered structure at the grain boundaries, there is a number of examples which are available where people have shown that the material becomes really soft. So, as a result, again we have a limitation on the Hall-Petch relation. So, Hall-Petch relation basically works in a domain, okay, of let us say something like about as large as a grain size, but not a single crystal of any grain size polycrystalline material, from that level up to around maybe about 50 nanometers or so. If you really go much below to around 20 or less than 20, you end up into problems. So, here we see one example where the strength improves to a large extent, particularly strength at high temperatures, by making a nanocomposite. This is an example of an aluminum alloy with the Al3Ti particles in it. These are nanoparticles. You can see the scale there is of the order of around 200 nanometers scale, in which if you look at individual particle sizes, they are of the order of around 50 to 20 nanometers. There are different sizes in the range of 20 to 50 nanometers. So, such nanoparticles, if they are embedded in an aluminum matrix, and these particles are ordered Al3Ti particles. These are FCC ordered structures which are called the L12 structures. When we come to intermetallics, we will talk more about what is this L12 structure. Basically, if you take an FCC structure, order it, okay, in such a way that all the face centered atoms are occupied by one type of atom and all the body corners are occupied by one type of atom, this is what is called an L12 structure. in an Al3Ti you have 3 atoms of aluminum, 1 atom of titanium, and the titanium occupies all the body corners and the aluminum occupies all the face centers. That is what is called an FCC ordered structure, and such an ordered structure, if you subject it to a diffraction, you will see, if you look at any of these 2 diffraction patterns, you will clearly see there are faint spots in addition to the major spots which you can see there. For example, the top one gives you a three-fold symmetry or the 6-fold symmetry, which is characteristic of the 111 pattern, and you have fine spots at the center, and those fine spots are what are called the superlattice reflections. We know in an X-ray or electron diffraction, in any diffraction, whenever you have an ordered structure, you get extra peaks or extra spots which correspond to the ordered nature of the particular compound. So once a compound is ordered, you get extra spots because of the ordered nature, which I think we will talk at some point of time, probably in anybody has done X-ray course here? Okay. So have you heard about superlattice refractions? Okay. For example, in FCC, what kind of superlattice refractions you can expect? What are the fundamental refractions in FCC? In FCC, 3, that is for h square plus k square plus l square. So if you look at the real HKL, what are the peaks that you can get? 111 peak and 200, 220. These are the first 3 peaks that you can get in FCC, and the 110 peak and 100 peak, these 2 peaks are the forbidden peaks in case of a disordered FCC. The moment you order it, okay, the structure factor changes, and from the structure factor one can really prove that you can see the 100 and 110 reflections as superlattice reflections in an FCC structure. Similarly, in a BCC structure, you don't usually see the 111 peak under the normal conditions if it is a disordered structure. Once you make a BCC into ordered BCC, then you can even see the 100 and the 111 peaks in a BCC. Here is an FCC structure which is an ordered FCC structure, and all those faint spots that you see are the superlattice reflections. The only difference between superlattice reflections and the fundamental reflections is that their intensity will be very low, because their structure factor is usually the difference of the atomic scattering factor of the 2. Okay? And because it is a difference and intensity is nothing but the square of the structure factor, so you will see that the intensity of a superlattice reflection is much smaller than the intensity of a fundamental reflection, which is nothing but the summation of the atomic scattering factor of the 2 elements.
So extra lines are visible from that only, we can say?
Yes, from the extra lines one can see, but the important thing is that the extra lines are so faint that in some cases you may not even see. For example, if you take copper zinc, a typical example of brass, we all talk about beta brass. Beta brass can be ordered at high temperatures, around 550 degrees or so. Okay. If you take to a temperature below 550, you have usually an ordered BCC structure, which is beta prime, people call it, or beta dash, and if you go to higher temperature, you talk of disordered structure. And if you compare the crystals, the diffraction patterns of these 2 by X-ray, you will not be able to see any difference, basically because copper and zinc are next to each other in the periodic table, and the atomic number difference between these 2 is just 1. So as a result, if you consider the structure factor difference is basically 1. So if you talk of the intensity, intensity is nothing but the square of the structure factor of the superlattice reflection by the fundamental reflection. If you look at the square of these 2, okay, and this is atomic size difference is only 1, whereas this is nothing but the summation of the 2, which is 29 plus 30, the atomic numbers is 59. So it is 1 by 59 square of it. You can see the intensity ratio between the fundamental reflection and the superlattice reflection for a BCC structure like such as the copper zinc beta brass is so small that one cannot really see the superlattice reflection if you use an X-ray. One can go to electron microscopy where the incident beam itself has so much high energy because you are using about 100 kilovolts there. So, because of which you are able to see the superlattice reflections also more easily. Otherwise, if you go to other compounds which are also probably BCC based, but the two atoms are far apart in the periodic table. For example, nickel aluminum, NiAl, you must have heard of NiAl, is also a ordered BCC structure, and such an ordered BCC structure there you will be able to easily see it because nickel atomic number and aluminum atomic number are vastly different. So, you can easily see the fundamental reflections and the superlattice reflections in such a case. So, one has to remember this aspect. So, these superlattice reflections always have a lower intensity because, as I told you, the structure factor basically is different for a superlattice reflection. For a fundamental reflection, structure factor is much bigger than that for the superlattice reflection. But what is more crucial here, because we are talking about the nanomaterial, is that when you put such an ordered nanoparticle in an aluminum matrix, you see a much higher improvement in the strength, particularly at high temperature. For example, if you look at this plot, which shows the hardness, Vickers hardness of a commercial aluminum alloy 2017 alloy, which is nothing but an aluminum copper alloy. The most popular aluminum alloy for an aerospace industry is the aluminum copper alloy, you all know that. Okay? If you take such a aluminum copper alloy, take it to the peak aged condition and look at its hardness as a function of temperature, you will see that its hardness falls very rapidly because we talked about it in the last class. Why does the aluminum copper alloy lose its strength when you go to higher temperature? Because of the particle coarsening or particle dissolution, isn't it? These are the two crucial important parameters which affect the strength of the aluminum alloy at high temperature. The particles which are the theta double prime or theta prime that we talk about, either they coarsen or dissolve depending on the temperature, because of which the strength more or less drastically falls. But if you take this kind of a composite, nano composite, you see that these Al3Ta nanoparticles remain inside the aluminum matrix without any dissolution or coarsening, and then can give you strength at even temperatures of the order of about 500 degrees. You cannot imagine using an aluminum copper alloy at 500 degrees, impossible. The maximum temperature is about 300. Nobody can imagine using an aluminum copper alloy at high temperatures. That is why there is a lot of work nowadays on trying to develop high temperature alloys using such composites structures, nano composite structures. Okay? So, this is one of the advantages of the such a nano composites. Other thing is also there is another example here, aluminum iron alloy, where what we see on the left side is nothing but an aluminum iron nano composite which is compacted and gives you an idea of what are the densities that are achieved in the green condition, that means as compacted condition without any sintering, that you reach densities of the order of around 80% or 85%, and such a green compact, if you look at the hardness of it, you see that the hardness you can reach almost about 2 gigapascals, which is very high for any aluminum alloy. These are just green compacts even without sintering. So, one can achieve such high strength levels in a nano composite. So, that is one of the fundamental reasons why everybody is excited about nano composites as far as metallurgical applications are concerned. Yes, physical properties are also much improved properties people have found, but as a metallurgist we are more concerned about how to improve the strength of a material, okay, and how to control the microstructure of a material so that you can achieve a particular mechanical property, enhanced mechanical property. This is one of the things. You may also ask me, what about the creep resistance in such a nanomaterial? We will talk about it when we talk about grain coarsening in these materials and how to control the creep in such materials, because we know that if you have a fine grained material, the material easily creeps. Okay, so at high temperature in principle you should lose the strength, but in some of these materials even the high temperature strength, as I showed you in the previous case, is also much higher. How is that you are able to achieve such high temperature strength, okay, without any creep occurring? That is basically because when you put these hard particles, okay, they not only coarsen because their solubility in aluminum is very small. You have to remember that the coarsening of a particle has a direct relation to the solubility. For example, in dispersion strengthening, the particles do not coarsen, isn't it? When I put yttria into a nickel based superalloy, the particle remains what they are. Whatever you have put, they don't coarsen, basically because yttria does not dissolve into nickel. So the coarsening is largely related to the dissolution, because coarsening occurs by diffusion. Particle coarsening, if at all particle has to coarsen, the atoms have to diffuse, okay. So that is related to the dissolution or the solubility of any of the element inside the particle, okay. For example, in case of the aluminum copper alloy, the particles that are coming out are basically Al to Cu, okay. So it's the solubility of copper in aluminum which controls the coarsening. Of course, the diffusivity also is crucial, okay. The temperature is also crucial, but at the same time one of the most important parameter is the solubility. So if you take those systems where the solubility is very much restricted, then in such systems the grain coarsening or the particle coarsening can be controlled. This is one of the reasons why if you have such Al3Ta nanoparticles, they do not coarsen, at the same time they act as spinning agents for any grain boundary sliding, which is the phenomenon for the creep. So you can control the creep. So one is able to achieve high strengths in these materials even at high temperatures by controlling the grain boundary sliding, okay. So that is one of the advantages in these materials. There are also additional things when you go to a nano regime. One can achieve wide range of phase fields. For example, if you talk about the solubility of a metal A in another metal B, this is decided usually by what is called the Hume-Rothery rules. We all know about them, isn't it? The 4 Hume-Rothery rules, which are crucial in deciding the solubility. And this is true also for intermetallic compounds and also for the solid solutions. And this can be extended when you go to a nano regime. How do we extend it? We can extend it because the grain boundaries volume fraction increases to a large extent. We have talked about it in the previous class, and when you increase the grain boundary volume fraction, and we know that grain boundaries are more open structures, when you have such a large fraction of open structure in a material, the solute atom can easily dissolve. Why is that? The solute atom, there is a restriction on the solubility, because whenever a B element dissolves into a element, we know that the atomic size of B is different from that of the atomic size of A, and as a result when you put a B atom into an A atom, there is a stress involved. For example, if you look at the atomic arrangement, for example something like this, A type of atoms, and if you have a small B atom which is not really interstitial but at the same time substitutional, but its size is smaller than the remaining atoms, then you see that the moment you put a small atom there, the other atoms around it are attracted towards that, because there is always some kind of a delta H mixing associated with any A and B atoms, and because of that there is either an attraction or a repulsion depending on the situation, whether it is delta H mixing is positive or negative. Okay, we know about it in the thermodynamics class, we have talked about it. And so if you look at such a situation, this when the atoms are either attracted or repulsed, there is some strain that is associated with it, okay. And this kind of a strain prevents more dissolution, because whenever there is a strain inside the lattice, okay, the lattice becomes unstable. So as you put more and more atoms into it, there is more and more strain, and the moment the strain crosses a particular critical value, then the solubility, there is, you reach a maximum on the solubility, that what we call the solubility limit has been reached. And so as a result, for any given crystal structure, there is a maximum solubility for a particular solute in a solvent, and this basically depends on the atomic size difference between the A and B, what is called the misfit parameter, okay, size factor people call it. So as a result, here whenever we talk about two elements in a normal crystal, okay, where the atoms are periodically arranged, in such a case there is a restriction on the solubility of a B in A. But the moment you have a random structure, obviously such a strain generation, you cannot expect a lot of strain being generated, because the atoms are randomly arranged. So as a result, there is no real pushing of atoms when a large atom is sitting, large solute atom is sitting, or the atoms being pulled to a large extent when a small atom is sitting, because the total strain gets uniformly distributed inside the material when you have a random arrangement. This is true in the liquids also. We always see the solubility of a particular solute in a solid is much lower than in a liquid. Why is that so? The same thing, that in a liquid there is no strain generated when a solute dissolves, so you can have a larger solubility in a liquid. Exactly similarly, because the grain boundary structure is similar to that of a liquid structure, is like an amorphous structure, you can expect a large solubility. That is why in most of the cases we will also see in the coming slides that the solubility can be enhanced to a large extent. And here is an example of a nickel aluminide NiAl intermetallic compound. We just now talked about it, the B2 type of a compound, that means ordered BCC compound, which under equilibrium conditions, you see the phase diagram, the solubility is from about 45% to about 55%. So the room temperature solubility, if you look at it, not really room temperature, we have the phase diagram only up to 400 degrees centigrade, but if you go to lower temperature, it further gets reduced. Okay, we know that solubility is much lower at low temperature and usually increases at high temperature, basically because the lattice expands. When the lattice expands, the system can accommodate more strain, so more solubility can be achieved. So as a result, if you see, the solubility is higher at higher temperature, and at low temperature it is much smaller, and that is from 45 to 55. But the moment I make them in a nanocrystalline form, what you see the picture on the right side, the nanocrystalline NiAl made, and its solubility range varies from about 25% here, the bar which is given on the bottom, please have a look at it, and the phase field of NiAl varies from about 25% to about 65%. So one can have a very wide range starting from 25% of nickel to about 65% of nickel possible by just making it nanocrystalline. Okay, so one can increase the solubility. You may say, what is the kind of advantage that I get by doing that? The advantage that I can get is that NiAl, if I want to produce it, okay, I can produce it only in a limited range. There are a number of intermetallic compounds particularly which are called line compounds. Are you aware of them? What are line compounds? Fixed composition, correct. Their composition is fixed. They have a very narrow composition range, and such compound, if you want to make it, it is very difficult because you have to control the composition carefully so that you have exactly that composition. For example, Fe3C, you take it, cementite, it is a line compound. Mg2Si is a line compound. There are so many line compounds like that. Al3Ni is a line compound. These are all line compounds with fixed compositions. If you want to make them under normal conventional conditions, you have to really control the composition so that exactly you are at that composition to get that compound, single phase compound if you want to make. But if you go to the nano regime, even if the composition is slightly on the either side, you can still produce that particular compound because that compound can exist over a range of composition. One can produce such compounds over ranges of composition, and one can extend the phase fields. Okay, one can have large phase fields possible in this kind of thing. And when we are talking of solid solutions, what is the advantage of extending the phase field in case of a solid solution? If you have an extended solubility, what kind of an advantage you can get?
will have more strengthening.
More strengthening, not only because of solid solution strengthening, but also you can precipitate larger volume fraction of the precipitate, because the volume fraction of the precipitate that you can generate at any given temperature during aging depends on the solubility. Okay. For example, if you look at this, the typical aluminum copper phase diagram, we know that if I take this alloy, if I am doing aging at this temperature, if I take these two alloys, alloy number 1 and alloy number 2, in alloy number 2 I can have a larger volume fraction of the precipitate when compared to alloy number 1, isn't it? So that means if I can have a supersaturated solid solution with higher amount of solute, then in such a supersaturated solid solution, if I can do aging, I can have larger volume fraction, and the volume fraction, if it is higher, I can have higher strength. So if I can have a higher supersaturated solubility, okay, an extended solubility, one can have not only an increased strength because of the solid solution formation itself, but solid solutions we know always have a lower strength when compared to a precipitation hardened alloy or a dispersion hardened alloy, isn't it? So as a result, one can increase the strength of the solid solution by precipitating a larger volume fraction of the precipitate if we can have an extended solubility. Okay. So that's why the extended solubility not only has can give you an improved strengthening, but also can help you in producing these compounds over wide ranges, particularly in case of line compounds where you have a limitation in making. For example, Al3Ni, we have a lot of problem in making Al3Ni because aluminum has a low melting point, nickel has a very high melting point. Okay. If you want to make them by melting route, okay, you have to melt aluminum and nickel together, obviously, then you form a compound in the liquid state and then cast it so that you can get a Al3Ni compound. If you want to make such a compound, okay, by the time the aluminum starts, the nickel starts melting, there is a chance that some of the aluminum starts boiling. So it is very difficult to control the composition. Okay. How do you know how much of aluminum has boiled? So that if you want to know make Al3Ni, you need to know how much of aluminum you should take, how much of nickel you should take, so that both of them can give you the Al3Ni single phase compound. And there is a lot of difficulty by such a normal conventional routes to make the single phase compounds which are particularly line compounds. Whenever the situation is such that one of the element has a much lower melting point when compared to the other, the problem gets aggravated in these cases. Even otherwise composition control, okay, is very difficult during the liquid metallurgy route, because we always know that during solidification there is always segregation that occurs. Okay. So once the segregation has occurred, then it becomes very difficult to produce a particular composition, and ultimately you may not end up in a single phase, but you end up in a two phase mixture, and if your goal is to make a single phase, you have a problem in making it. So as a result, nanocrystalline materials have an advantage. One can have a wider range of composition and still have such a compound formation. One can also do a lot of thermodynamics, and to show that yes, if you take it to a nanocrystalline state, one can have a wider composition range. Okay. For example, one can calculate the free energies of the nanomaterials, okay, particularly in case of metallic materials. It is very easy to calculate the free energies. We have talked about it in our thermodynamics class, and show that when you decrease the crystallite size, the plot on the right side, if you have a look at it, when you decrease the crystallite size, what you see is the phase field of, this is the phase field of NiAl. We are showing that the distance between the two curves gives you the composition range over which NiAl can be stable, and that composition range becomes larger and larger if you come to lower and lower crystallite size. Okay. And when you reach a crystallite size of about 5 nanometers or so, which is what has been shown to you before. For example, if you look at the previous lecture, most of the particles are of the order of 5 to 10 nanometers, and if you look at such a fine particles, okay, of 5 to 10 nanometers, their phase field extends from almost 28% to 68%. Okay. So, which is what we have observed under experimental conditions. So, one can do thermodynamics and show that what you see experimentally is not anything which is unexpected, but from thermodynamics one can really prove that such a thing is possible. One can also produce very fine particles. For example, this is another example of a nickel silicide. Okay. Nickel silicide, which is called a gamma phase, Ni13, 31 Si12 phase, which is called a gamma phase. One can produce a very fine particles of them, and what is important is that this is produced by a technique which is what is I called you top down approach. That means you take a macro crystals and break them down by what is called a ball milling technique, and you can see with increasing milling time one can decrease the particle size and reach a level of almost about 10 to 15 nanometers. And what is important is that such phases such as these intermetallic compounds form only when the crystal size comes to a size of around 20 nanometers. If you start with nickel and silicon, let us say, and start doing milling them together, you have a nickel powder, silicon powder, putting them together and doing ball milling. And if you do that, when you bring the crystal size of nickel to a level of around 20 nanometers, that is the time when suddenly there is a reaction between the nickel and silicon and the intermetallic compound comes out. So, in a nanocrystalline state, the formation of intermetallic compounds largely depends on what is the crystallite size, because below a certain crystallite size, okay, the surface area to volume ratio is so large, the particles become unstable and start reacting with the environment, whatever is there around it. In this particular case, silicon is there around it, and it reacts with that silicon and then forms a compound which is more stable under this particular, at that composition under equilibrium diagram. If you look at it at that particular composition of about 25%, what phase is more stable? If you look at it, that is the phase which forms by such a reaction. But what is crucial to understand is that this always happens only in a nanocrystalline state. Okay. So, making nanocrystals is crucial for such compounds.
So, is this mechanical alloy?
This is mechanical alloy. Yes, this is what is called mechanical alloy. We will talk about it a little later. Today I do not want to bring that into the picture, because let us take it generally as nanocrystals and then look at how these nanocrystals have interesting features when you take any material into a nanocrystalline state. This is another interesting feature, that when you see a phase diagram, there are many phase diagrams where you see a large number of intermetallic compounds. This is one such phase diagram, which is a nickel silicon phase diagram, which has a number of compounds which are shown there. Beta 1 phase, which is nothing but Ni3Si kind of phase, and then you have a gamma phase, you have a delta phase, and you have an epsilon phase, you have NiSi phase, and you have NiSi2 phase, a number of intermetallic compounds. But there is a difference between these compounds, that some of these compounds are congruent melting compounds, some of them are not. What is a congruent melting compound? A compound which melts at a fixed composition is called a congruent melting compound. So, in this phase diagram, if you look at it, there are basically only 3 congruent melting compounds. One is the gamma phase, another is the delta phase, and finally the NiSi phase. Only these 3 are the congruent melting compounds, whereas the other compounds such as NiSi2 or beta phase, all these phases are non-congruent melting compounds. Usually a congruent melting compound has always a large negative enthalpy of mixing, because up to the melting point it is not changing to anything else, it is able to be stable up to the melting point. This happens only when the delta H mixing is largely negative. So, when you look at such intermetallic compounds which has a large negative enthalpy of mixing, they are very stable compounds, and in a nanocrystalline state not every compound becomes stable. When you take A and B elements, bring them into nanocrystalline state, and A and B have to react with each other and form some compound, the compound that forms is always that which is a congruent melting compound near that particular composition, whatever composition you have chosen, and not a non-congruent compound. For example, if I take nickel and silicon in the ratio of 3:1, okay, Ni3Si, okay, at the Ni3Si composition in the phase diagram, what I have is a beta phase, and beta phase is not a congruent melting compound. So if I take a 3:1 and take them to nanocrystalline state, what I see is that beta phase does not come out, but whatever is the closest composition congruent melting compound, that is the compound which will come out. That compound is nothing but the gamma in this particular case. That is why in the previous case what you have seen is the composition that we have chosen is Ni 25% silicon, which is the Ni3Si composition, but the phase that is forming is really a gamma phase, which from the diffraction pattern one can prove it, X-ray diffraction also one can do and can prove it. And so you can see that true not only in case of gamma, but also in case of delta and also in case of NiSi. So what you have on the right hand side is a kind of a metastable phase diagram, okay, because nanocrystalline materials are metastable, isn't it? Okay. So in a nanocrystalline state, the equilibrium phase diagram is not always valid. It is not valid for one reason, that as I told you, not all compounds are feasible in a nanocrystalline state. We will come to it a little later. Thermodynamically we will try to show why not all compounds are feasible. And second is that when you have extension of solid solubility is possible, again we can see that the equilibrium phase diagram is not valid, because in a equilibrium phase diagram there is a limitation on the solid solubility, there is a restriction on the solid solubility, whereas when you take it to a nanocrystalline state there is an extension on the solid solubility. So you can generate newer phase diagrams, which one can call it them as metastable phase diagram. For example, what you have here is a phase diagram which consists of only 3 compounds. One is gamma, another is delta, another is NiSi, which are the phases which are possible under a nanocrystalline state, and all other phases one can remove it from that phase diagram and one can think of this. But one has to remember that it is still metastable. It is like our iron cementite phase diagram. We know that iron cement is a metastable phase diagram, and if you allow equilibrium to be achieved, ultimately that iron cementite phase diagram is not valid, and you have to talk in terms of the iron carbon phase diagram. So similarly, this is valid only as long as you are in the nanocrystalline state. Once you grow the crystals to a bigger size, then you revert back to the old phase diagram, the equilibrium phase diagram. This is true that in a number of systems. This is another system which is an iron silicon system. In an iron silicon system there is only one congruent melting compound, which is FeSi, and when you take iron and silicon into the nanocrystalline state, the phase that forms is always the FeSi phase, not all other phases which are existing in the phase diagram. Okay. One can prove this in a number of systems, and we have ourselves have done it in a number of systems. This is an example like that. So non-congruent melting phases are always bypassed when you go to a nanocrystalline state. Okay. This is also can be proved using thermodynamics, and one can talk about phase fields, okay, in a nanocrystalline state, what happens, and one can prove that only congruent melting phases are possible, okay, particularly because in the non-congruent melting phases always have a lower interfacial energy. Because of the large negative enthalpy of mixing, their interfacial energies are very low. In a nanocrystalline state, what is crucial is the interfacial energy. Okay. I think at some point of time I will just show you. Okay. Okay. Have a look at this picture. What you see here is that 2 phases, alpha and beta, okay, and we are plotting the free energy as a function of crystallite size. When we talk of stability of a phase, how do we define the stability of a phase? Whichever phase has a lower free energy, that phase is more stable, isn't it? That is how we define the stability of a phase. But whenever we talk of free energy, we usually talk of bulk free energy, volume free energy of a material. But when you take a material to the nanocrystalline state, we need to consider also what is called the interfacial free energy or the surface energy. If you add the surface energy to the system and then define the stability criterion, you will see that in the nanocrystalline state, if the G alpha plus G alpha interfacial energy, if that is lower than G beta plus G beta interfacial energy, then we can say alpha is more stable. Okay? If a combination of the interfacial energy plus volume free energy, if that combination is lower, that phase is more stable. If you look at two phases alpha and beta, it is possible that alpha is more stable than beta in a bulk state, that means when the grain size is very large, but the moment you take it into a nanocrystalline state, the beta may be more stable than alpha. Why? Because it is possible that alpha has a higher interfacial energy or a higher surface energy than beta. If the surface energy is higher, the free energy increases more rapidly as you decrease the crystallite size. Okay? So, when you keep on decreasing the crystallite size, the rate at which the free energy increases with decreasing crystallite size is a function of the interfacial energy or the surface energy. So, if a particular phase has a high surface energy, you will see its free energy raises very rapidly when compared to another phase which has a lower interfacial energy or lower surface energy, and you come across a critical point where the free energy of both the phases become equal, and below that particular crystallite size you will see the phase with a lower interfacial energy or the lower surface energy becomes more stable than a phase with a higher interfacial energy. In a nanocrystalline stage, the phase always that is stable is the one with the lowest interfacial energy, and the congruent melting compounds are one of those examples which have the low interfacial energy, and that is why you see that those phases only exist and the non-congruent melting phases do not exist. Same thing can be observed here. For example, you imagine there is a situation of three phases existing in a system, alpha, beta and gamma. Let us assume that gamma is a phase with a high interfacial energy. The moment I take this system into a nanocrystalline state, the gamma will have much higher free energy when compared to alpha and beta, and you see that in a bulk state you have a phase field of alpha gamma, gamma and gamma plus beta under equilibrium conditions, but the moment you take it into a nanocrystalline state, gamma goes to a much higher free energy level, that you have a situation of alpha plus beta being more stable than the gamma. Okay? So, this kind of a situation occurs. That is what exactly you have seen in the previous case, where the non-congruent melting phase, its free energy goes up and it is no more stable, and the congruent melting phase becomes stable, though at that composition in principle it is not supposed to be stable. Okay? For example, if you look at this particular composition where gamma should have been a stable phase, okay, you will see at that particular composition now instead of gamma it is a alpha plus beta mixture which is more stable. Okay? So, this kind of phase changes are possible in a nanocrystalline state because of the presence of congruent melting and non-congruent melting compounds. This is true not only in a binary case, in a ternary case also one can show that always only congruent melting phases are possible, and this is one example of nickel iron silicon and nickel iron aluminum, that always only the phases which are congruent melting forms. You can also produce nanocrystals in a quasicrystalline state. Okay? We talked so far about crystals which are in the nanocrystalline state. We can also have quasicrystals in a nanocrystalline state, and one can show with that such quasicrystals can have better properties, particularly physical properties. People have seen that such materials behave like semiconducting materials, and people are trying to use them as good semiconductors with better properties than the conventional semiconductors. Okay? So, you can see this case where you can have a nano particles of a quasicrystalline case, as I told you last class, that you can see that the diffraction obtained from a quasicrystal is entirely different from that of a crystal. Why? Because you have a special rotational symmetry in a quasicrystal, that is a 5-fold symmetry, and you can see here that you look at the transmitted spot and count the total number of diffracted spot around that, you see 10 diffracted spots, which is what is the 10-fold symmetry we call it, and that is the classic example of a quasicrystal. And these kind of particles can be made, and these particles one can show that they form at a fixed E by A ratio. We talk about E by A ratio as a crucial parameter in the formation of intermetallic compounds. Quasicrystals are also intermetallic compounds. Basically, most of the quasicrystals occur at fixed E by A ratios, and you can see that, for example, in copper zinc we all know copper zinc you have beta brass, you have a gamma brass, and you have an epsilon brass, which are all occurring at fixed E by A ratios. Okay, and you can see that this, in this particular case also, the quasicrystal, the volume fraction of the quasicrystalline phase keeps on increasing and reaches almost 1% when you vary the E by A ratio, and when the E by A ratio reaches about 2, you will see exactly that is the state at which you have the 100% quasicrystalline, nano quasicrystalline phase, which is possible under the nanocrystalline state. Okay, and they have, as I told you, a semiconducting nature, as you can clearly see here. If you take a mixture of aluminum plus copper plus iron, it will always show a metallic nature, that the resistivity increases with increasing temperature, which is the characteristic of every metal. Okay, but the moment you take these three and make it into a quasicrystalline state, immediately you see it will have a negative coefficient of resistivity as a function of temperature, that the resistivity decreases with increasing temperature, and in fact the resistivity increases with increasing volume fraction of the quasicrystalline phase, and also the negative coefficient of resistivity also increases with increasing volume fraction. Okay, so as a result one can really show that these nano quasicrystalline phases can have different properties than that of the normal metals. You are starting with the same metals, this aluminum, copper, iron, these are all metallic elements that we know, and they behave like a metallic nature when they are just in the mixed condition. But the moment all of them are brought into an alloy form with a quasicrystalline nature, but the moment you make this alloy into a crystalline nature, again you come back to the normal metallic behavior. Only when it is in the quasicrystalline state it behaves in a semiconducting nature. Okay, we will stop at this point and continue in the next class.